In December 2019, China notified the World Health Organization of several cases of human respiratory illness, a disease later named COVID-19. The virus causing this disease is known as severe acute respiratory syndrome coronavirus 2. The disease spreads through small droplets that are expelled from the nose or mouth when a person with COVID-19 coughs or exhales. Therefore, standing close to someone who is infected can put you at risk. These droplets can land on your hand and be transmitted through something as simple as a handshake, if afterwards you touch your eyes, nose, or mouth, the so-called T-zone. The virus is known to survive on different types of surfaces, so touching these contaminated surfaces and then touching your T-zone brings a high risk of infection. What we know so far: the coronavirus is spherical in shape, and its genetic material is encapsulated by different types of proteins. Some of the key structural ones are spike S protein, the most prominent feature of coronaviruses from where they get their name, then M, or membrane protein, and the so-called envelope protein.
Assalamu alaikum. I'm Nazmul Shahid and welcome to my online class. I am a lecturer in physics under the Department of Physics in Boyshall Cadet College. Today I discuss chapter number 6, that is geometrical optics. And this is the first class. And by the end of today's class, cadets, you will be able to, number 1, explain reflection of light and mirror. Number 2, explain refraction of light. Number 3, explain the general form of Snell's law. Number 4, explain diffraction of light through a medium confined by two parallel surfaces. And number 5, explain the Fermat principle. And this is the last points. Before entering the chapter, that is geometrical optics, I discuss the nature of light, because today we discuss the different properties of reflection and diffraction, and this is the one kind of properties of light. And light always time shows dual natures, and only one light shows the dual nature in physics. Sometimes light shows as a particle nature, and sometimes shows it's a wave nature. When particle hits any kind of surface and produce heat there the light shows its particle properties, and when light travel from one medium to another medium and never produce heat, there it shows its wave properties. And there are too many theories about lights, but here I show you 4 kind of theories that given by Newton's, Christian Huygens, Thomas Young, and Einstein. Newton said that when we see a particle, the particle emitted lot of particles, that is light particles, and that in turns our eyes, and we see this particle. And Christian Huygens argued that light might be some sort of a wave motion. Then Thomas Young provided the first clear demonstration of the wave nature of light because of their interference properties. And lastly, Einstein proposed an explanation of the photoelectric effect that used the idea of quantization. And we know that the quantization model assumes that the energy of a light wave is present in particles is called photon. Now I discuss what is reflection and the law of reflection. Firstly, I give you the definition of reflection of light. When light rays fall upon a surface and it bounce back in a particular manner, it is called reflection of light. The plane surface that reflection light regularly, it is called mirror. And in these pictures, I also show you this phenomena. And this is the incident ray. It's fall upon a plane surface and it's reflected in this way, and this is called reflective ray. And this is the normal to the surface, and the incident ray make a angle to the normal, that is called incident angle, and when the reflected ray make angle to the normal, that is called reflected angle. And we know that there are two laws of reflection. Number one, incident ray, reflected ray, and the normal above mirror all remains in the same plane. And the last one, that is the second one, angle of incident and angle of reflection are always time equal. That is, theta I is equals to theta R. Now I show you there are two kinds of reflection, and this reflection varied for the reason of the surface. You see here, this is a smooth surface, and there this is the rough surface. In smooth surface, there are always time incident angle and reflection angle is equal. That's why it's called regular reflection. But if the surface is rough, then the incident angle and the reflection angle never be equal. And this kinds of reflection is called diffuse reflection. I also show you two exactly and practical pictures of regular reflection and diffuse reflection. From these pictures, you very much clear about the regular reflection and diffuse reflection. Now I discuss mirror. Firstly, there are two types of mirror. One is plane mirror, another is spherical mirror. In this picture, I show you a plane mirror, and the definition of plane mirror is the smooth plane surface that reflect light regularly. It is called plane mirror, and the size of the image is always time equal the size of the object. And this is the properties of plane mirror. And in the first picture, I show you if a point is standing there, then the light ray comes to the eyes, and it always time show the opposite side of the mirror, that is a virtual image is formed in the plane mirror. Now I discuss spherical mirrors, and the definition of spherical mirror is the smooth spherical surface that reflects light regularly. It is called plane mirror. And uh, if you look at the pictures very carefully, you know that this is a convex spherical mirrors, and the definition of convex spherical mirror is a convex mirror is a curved mirror in which the reflective surface brought towards the light source. That's meaning the outer surface of a spherical mirror is convex mirror if it reflects light. And from these pictures, I show you this is the principal axis, and when we see any kinds of objects, these objects uh, is viewed as like this. And we also know that the focal point is equal to r by 2. That is the half of the radius of curvature of the spherical mirror. And here I also show how to they work, that is convex spherical mirrors. If you look at the pictures very careful, then you can clear understand for the image formation of convex spherical mirrors. Here the incident ray is parallel to the principal axis. It's come to the mirror and bounce back, and incident angle and deflection angle are also same. And if the deflection angle backed in the principal axis, then it must be meet to the focal point. And if it is parallel, it always time meet to the focal point. And this is the radius of curvature, and we know that the relation of focal length and radius of curvature, the focal length is always time half of the radius of the curvature. Here I show you a practical situation of a convex spherical mirror, and this is I show you the size of the object, and this is the size of the image, and you see that the size of the image is smaller the size of the object. And the principal ray of convex mirrors are a ray parallel to the principal axis is reflected as if it come from a focal point. Number 2, a ray along a radius is reflected back upon itself. Number 3, a ray direct towards the focal point is reflected parallel to the principal axis. And lastly, a ray incident on the vertex of the mirror reflects it an equal angle to the axis. And here I show you the image formation of convex mirrors. Now I show you a concave spherical mirrors, and the definition of concave mirror is a convex mirror or converging mirror has a reflecting surface that blocks inward. So the inner surface or the concave surface of the spherical mirror is called concave mirror if it reflects light. So you see, this is the exact situation, and this is the geometrical situation where we draw the image or formation of ray diagrams, and this is the actual pictures. If you see here, this is the practical situation. We generated 4 light sources, and it must be parallel to the principal axis, and it must be meet at the focal point. And this is the practical image formation of concave spherical mirror. Here we see that the size of the image is larger than the size of the object at general form. And this is the real pictures format. And the principal ray of concave mirror is a ray parallel to the principal axis is reflected through the focal point. A ray along a radius is reflected back upon itself. A ray along the duration from the focal point to the mirror is reflected parallel to the principal axis. And last, a ray incident on the vertex of the mirror reflected at an equal angle to the axis. And this is the image formation pictures, and cadets, you must be see these pictures, and using this way we you draw any kinds of practical problems in geometrical optics. And this is the practical use of concave mirror. You see that the face of the girl is larger when she see her face in the mirror. And this is the practical situation. I show you why the image is larger than the objects. This way, uh, concave mirror used to make the larger image. And the sign convection of the mirror is when it is positive and negative. This is means sign conventions. Object distance is always 10. It's never. Image distance is P. Object distance, that is object distance P. This always time use is P. It's never, that means you can use or not, that is your own problems. Image distance Q, this is real image, and this is virtual image. And the focal length in converging mirror F is equal to R by 2, and diverging mirror F is equal to minus half of R, and magnification upright image and inverted image. So where the property shows in mirror, that is called sign convention. If the definition comes, what is sign convention? The sign convention is defined where we show all kinds of properties of that matters. Here the matter is mirrors. So again, I alarm you for coronavirus. Always time stay at home. Avoid touching your face, that is mouth and eyes. Frequently wash your hands, and always time avoid contact with other persons. And if we maintain these things, we must be fight against the coronavirus, inshallah. Now I discuss refraction of light. And we know that refraction is a phenomena of changing the path of light as it travels from one medium to another medium when the ray of light is incident obliquely. This is very important. If it is perpendicular to the surface, their reflection occurs, no kinds of refraction occurs. So when the incident ray falls upon in a surface in obliquely, then the refraction occurs in that surface. Here I show you these two medium, rare medium, and this is denser medium. When a light ray comes to the rare medium, it bends toward and denser medium. Then again, when this light passes the rare medium, it again changes the direction of the path. Okay, so here I show you this is the incident angle and this is the refraction angle. Here the refraction angle, here the incident angle. Because two mediums is same, there's rare, so the incident angle on the both sides is same, and the inner angle, that is refraction angle. And this is rare medium, this is denser medium, and we know that when a light enters from rare medium to denser medium, this light ray come close to the normal, and when the light goes denser to rare, then it's far away from the normal. And we know that the two kinds of law of refraction, the incident ray at the normal to the refracted surface at the point of refracted ray are all lie in a same plane. And second law, for a given pair of medium for a light of a given wavelength, the ratio of the sine of the angle of incident to the sine of the angle of refraction is a constant, and that is called Snell's law. And we know that Snell's law mu is equal to sine I by sine R. And this is a one kind of practical situation I show you. And this is the relation between velocity and the Snell's law. If the incident angle is theta I and the refractive angle is theta t, then the Snell's law is sine theta I by sine t, that is lambda I by lambda t. Why it is lambda I by lambda t? That is lambda means we know that v by f, that is v is equal to f lambda from equation. So lambda I by lambda t, that means vi by f and vt by f. The frequency is same because we use a one source of light, and one source of light have same frequency. So f is missing. So lambda I by lambda t is equal to vi by vt. And we also write here, and we know that eta is equal to c by v. So we write here that is theta nt by ni. We know that in the Snell's law, ni sine theta I is equal to nt sine theta t. From this equation, so we can write that lambda I by lambda t from sine theta I by sine t. And here, this is a practical situation. If the angle is 30 degree, then the refraction angle is 19.2. This is the mathematical problems. And we know that this is air and this is glass, and the refractive angle of air is 1 and the refractive angle of glass is 1.52. So we know that is in previously I show you theta 1, that is refractive angle of incident angle sides, is equal to refractive angles of refractive side, that is theta 2, and the refractive index. So from these equations we use, and we get the ultimate result of refractive angle, that is 19.2. This is a very easy mathematical problem I show you. And here I discuss the refractive index. The tips is refractive index of a optically rare medium is lower than that of the denser medium is higher. Mu of a denser medium, we can write that rare medium is more than that of rare medium, that's why denser medium is less. In refraction, the velocity and wavelength of the light is changed. This is very important. In refraction, the frequency and the phase of a light do not change. So 3 and 4 point you must be memorized. And number 5, A mu m is equal to Ca by Cm, we know that, and A mu m again with respect to wavelength lambda A by lambda m. So you see here A mu m and lambda A by lambda m. If mu is left hand, then it is upper, and A is left hand, that lambda is upper, and the m is right hand, so lambda is lower. And the principle of reciprocity of light, we know that this can will be happened here. and this is incident angle, this is refractive angle, and we know that A mu B is equal to sin I by sin R. So if we convert it B mu A, then sin R by sin I, and if we multiply these problems, then we can write that A mu B multiplied by B mu A, its result is 1, or A mu B is equal to 1 by B mu A. So you must be memorize these kinds of formulas. That is A mu B multiple B mu A is equal to 1. Now I discuss refraction through a parallel slab, and this picture shows that is the refraction through a parallel slab, and here I also show you the same kind of pictures, and that is the ray diagram, and I consider there is a rare medium and there is the denser medium, and rare medium consider A and the denser medium consider B, and the thickness of the parallel slab is T, and when a incident comes and it's bands, and again it's bands, and if there are no medium, then the light must be goes a straight line. So from this picture you see that the light phase is bent, and this is the normal drawing for two kinds of incidents, and we know that the incident angles I1 and R1 in this sketch, and in this case I consider I2 and R2. That is, it is parallel slab. For these reasons, there are two kinds of I1 R1 and this is I2 R2. And if we take the equations, that is A mu B sine of I1 by R1, and if we take the equation B mu A, when the light rays goes denser to rare, then mu A is equal to sine of I2 by R2. And we know that in the previous slide, A mu B multiply B mu A is equal to 1. Now we put the values here, and we know the result is 1. And here must be I1 and R2. R1 is not equal. That's why I1 and R2 is not equal. Now I show you the physics at home. Look at the two pictures. In the first picture, the mug is empty, but inside of the mug there is a coin as like this, but we cannot see here. But when we fill the mug with water, then we can see the coin. And why it is possible, I show you in the side of the pictures. So this is the example, practical example, it at home. And now, lastly, I discuss that is Fermat principle. Why Fermat principle is very important? Because we know that there are two laws of reflection and two laws of diffraction also. But where is the proof is coming from these two laws? These two laws proved both in reflection and diffraction comes from Fermat principle. But before entering the Fermat principle, I discuss shortly Hero's principle, because for giving the description of Fermat, Hero also described these theorems before, but he cannot prove it, and Fermat show the proof of these two laws, both in reflection and diffraction. Hero said that the path taken by the light is going from some point A to another point B via the reflecting surface is the shortest possible one. And I show you the pictures, and this is the smooth surface, and this is the incident ray, and this is the reflective ray, and the point of A is here and the point of B is here. If the light goes this way or light goes this way, there are two paths. So the light must be taken the shortest path that said by Hero's theory. So light must be in trans firstly comes to A to O and then goes to O to B. And lastly, I describe that is Fermat principle. When a light ray travels between any 2 points, its path is one that required the least time. So you see the pictures very carefully. Uh, the point of initial P and the last point of Q, and the distance between them is D, and the incident point at that point, and the initial distance from the initial point to the incident point is x, and the rest of the distance is t minus x. And we consider here the height of P point from the normal. There is the separation between two medium is A, and the distance between Q to the separation between two medium is P. Now we know for the velocity equation V is equal to S by T, the total time taken for going to light rays P to Q point, there's two times for the times P to incident point and then incident point to Q2. So for this total point time T is equal to R1 by V1 plus R2 by V2. And we know that for the distance, that is R1 and R2, find out for R1 and R2, we take in our Pythagoras theorem, and we written that R1 is equal to root over a square plus s square, and R2 is equal to that is root over b square plus t minus x whole square. And we know that velocity v is equal to c by n1, and v2 is equal to c by n2. And if we discuss briefly the Fermat principle, so total time T is equal to S1 by B1 plus S2 by B2, and we know that with respect to diffractive index, N1 S1 by C1 plus N2 S2 by C. So velocity of light is all medium is same, so we consider 1 by C, and for applying the Pythagoras theorem, we written that n1 root over x square plus d1 s square plus n2 root over l minus x whole square plus d2 s square. And the theorem of Fermat, he said that light goes this path where it needs least times. So least time tends to 0. Now I divide it or differentiate the equation dt by dx, that is 0 is equal to 1 by c, and for doing the differentiation of these equations, the result is n on x by root over x square into d1 s square minus n2 l minus x by root over l minus x whole square plus d2 s square. And the if we take the triangle p d1 and theta 1 angle, the sine theta on it must be equal to x by root over x square plus d on s square, and in the triangle of this and the angle of theta 2, the sine theta 2 must be L minus x by root over L minus x whole square plus d2 s square. So that's why we can write from the equation 1 by c theta 1 in sine into n1 minus n2 sine theta 2, and if we break the left hand side is 0, so c is equals to 0, then uh, we can written n1 theta n1 is equal to n2 sine of theta 2, and this is the initial equation of diffraction, that is diffraction index n1 sine theta 1 is equal to n2 sine theta 2, and this is the Fermat principle. That's why Fermat principle is very important for proving the second law both in reflection and diffraction. Now I give some knowledge-based question in this chapter. What does Fermat principle say? What is the principle of reflection? What are the two laws of reflection? What is the least time? What is the spherical refracting surface? And I show you some comprehension based questions, that is how does light know the shortest path? How do you show light reflection? How does light refract at a curved surface? How does the focal length of a spherical mirror change in water? Now I give you some MCQ questions. Characteristics of waves. The waves transfers energy from one place to another. The velocity of the wave depends on the nature of medium. The reflection, refraction, and superposition occur in the case of wave. And I show you the options. Another one, light is wave, longitudinal wave, mechanical wave, and electromagnetic wave. And the last question C, a glass lens of repetitive index 1.45 disappears when it immerses in liquid. What is the repetitive index of the liquid? And I show you the options. And I give you a homework. What is lens? We cannot discuss about lens. In next class, we must be discuss about lens. Explain why concave lens is known as diverging lens. What will be the position and nature of the size of the image for the given object? Explain in a suitable ray diagram. And number D, is it possible to get virtual image from the given mirror? Analyze with ray diagram. And this is the question answer session. If you have any questions and query, then ask me after the finishing today's lesson. I will reply you in dashboard. And with this hope, I, Nazmushit, conclude of today's lesson. Thank you all. And lastly, I show you a video clip for better understand of today's class.